In this lecture, we will consider some very simple circuits that contain an LTI capacitor. And we're going to study them to gain some familiarity with our device. Okay, LTI capacitor. This is our first example. Current source, an LTI resistor and an LTI capacitor are connected in parallel. Okay, so this is our circuit. This is one resistor. This is 1/2 farad capacitor. Okay, so this is the capacitor voltage, plus minus. Clearly, it's the voltage of everything because all three elements are in parallel. The currents are labeled as IR and IC. This is the capacitor current, and this is the resistor current. And this, the current provided by the current source, the independent current source, is a special one. It's a step-like current realized by our unit step function. It's only its magnitude is 3. Okay, 3 UT M. And we're asked to find the following quantities at time 0 plus. Okay, find VC 0 plus, IR 0 plus, and IC 0 plus for the following two cases. Okay, note that to be able to solve this circuit, possibly we need also one last piece of information. It seems that we know everything, but there isn't. And that one piece of information that we require is the initial voltage of the capacitor. Okay, and in A, it's given to be 0. Okay, therefore initially we're going to consider the case where the initially capacitor is empty or uncharged, and for B we consider the case VC0 minus is 4. Okay, now we already know what that 0 minus or something minus notation means. This means that the time just before 0, okay, it's arbitrarily close to, but a little bit earlier than t equals 0. Likewise, 0 plus means it's arbitrarily close to 0 from right. Okay, arbitrarily close to 0, but a little bit later than t equals 0. Okay, and the reason that the time t equals 0 is important is because this source is discontinuous at t equals 0, and because of the discontinuity of the source, it may be that there are some discontinuities. Well, it would be that certain variables, certain quantities could be discontinuous, and we're going to figure out whether that's the case. Okay, for those three variables. Okay, to help us in our analysis, henceforth we will be working with the following assumption, and that assumption is that capacitor voltage is always finite, okay, or always bound. In other words, the energy stored in the capacitor will always be bound, okay, or finite. Henceforth, we will assume that energy stored in a capacitor. Likewise, in an inductor, for when we start talking about inductors later on, or an inductor is always finite. This has an immediate consequence on the voltage of the capacitor or the current of the inductor, And for that, we have to remember what the stored energy was in a capacitor. It was 1/2 times the capacitance times the square of the voltage. If the energy is bounded or finite, it means square of the voltage must be bounded or finite, and that means the voltage itself must be finite at all times. Okay, so that's our assumption that we'll be working with. This assumption is not really necessary in order for us to reach the answer, but we're going to be making it because it simplifies analysis. Okay, so at least for this at this stage, this assumption will be useful for our analysis. But for later on, we will be able to drop it altogether. Okay, we will not be needing it anyways. So here is one way to approach the problem. Okay. Now consider the case A, where the capacitor is initially uncharged. Now, for time around 0, okay, from 0 minus to 0 plus, let's replace the capacitor with an independent voltage source. Okay. And this we can do thanks to substitution theorem. Okay, so what we mean by that is the following. Here we have the circuit. This minus VCT. 3T and 1. Here we have IR, and here we have IC. Okay, so we don't know at this point at least what the capacitor voltage does between 0 minus and 0 plus. But whatever it does, it will have some voltage, okay? And that voltage is the voltage given by this independent voltage source after the capacitor is replaced by the independent voltage source, okay? And thanks to substitution theorem, the rest of the circuit will not feel any difference. Everything else will be the same. IC, IR, and yeah, and that's pretty much it. This is also already 3T. Okay, so let's ask the following question. What do we know about VCT? What do we know about the capacitor voltage? And this assumption is where the answer is. We're assuming that the capacitor voltage is bounded. We're assuming that the energy stored in the capacitor is bounded. Okay? If energy is bounded, the voltage is bounded. So we call stored energy the capacitor 1/2 C, then you square the voltage across the terms of the capacitor. That's our stored energy. Hence, thanks to our assumption, finite energy implies or is equal to bounded finite VCT. Okay. So bounded means it can do all sorts of stuff, okay, in any given interval. It can reach perhaps very high values, but it will always be finite. Okay, it will not be arbitrarily large. The type of waveform that violates this boundedness would be, for instance, the behavior of the impulse function. If some voltage is in terms of, it can be represented by some impulse function, then clearly that's not bounded, okay, in an interval that contains the point which makes the argument of that impulse 0. Okay, and now what we're going to do is we're going to figure out the consequences of capacitor voltage being finite. And it turns out that that's a very That's the very thing that we need in order to be able to answer the question that we asked. So find that quantities. Now, our starting point is that VCT is bounded. Okay. So that implies, because everything is parallel in this circuit, the voltages of all the components are bounded. Okay. Now, especially voltage of this one on resistor is bounded, and therefore, by determining the equation, its current must also be bounded, okay, because current is the voltage divided by the resistance. So bounded capacitor voltage implies bounded resistor current. Then we can invoke KCL, and that implies 3UT equals IRT plus ICT. Now this we figured out is bounded because capacitor voltage is bounded, and 3UT we know that even though it's discontinuous, it's also finite, it's bounded. Therefore, something bounded equals something bounded plus something else, and that something else must itself be bounded. Okay, so this is bounded. IRT is also bounded, hence ICT is bounded. Okay. And that's the only thing that we have to know in order to be able to determine whether the capacitor voltage will experience a discontinuity or a jump at t equals 0. Okay, or t or at any time. So it's easy to see once we write the terminal equation for the capacitor. Vc0 plus equals Vc0 minus plus 1 over the capacitance, in this case 1 over 1/2. Then you're integrating from initial time to final time, and in this case the final time is 0 plus because we're asked for the value of Vc at 0 plus. And then what we do, we integrate the capacitor current. Okay. Now this is what? How can we determine the result of this integration? Because we don't know what ICT is exactly. Now this is special integral. It's special because the length of the interval of integration is infinitesimally small. Okay. And then the integrand is our capacitor current, which we know is bounded, and therefore this integral must give us this very simple answer. It must be 0, since IC is bounded. Okay. Now once again, let's try to see that this is 0 visually. Remember the Riemannian integral, definition of the integral. Okay, so what you have is you have a bunch of tiny rectangles, and then you figure out the areas of those rectangles and you sum the area, and that gives you, in the limit, the integral. Now, this integral from 0 minus to 0 plus can be thought as integral from minus epsilon to plus epsilon. Epsilon is a positive number, and what you do is you keep squeezing epsilon further and further. So this becomes smaller and smaller. Okay, this thing you're squeezing the length of this interval. Okay, and in between is your ICT. Okay. Now you don't care exactly what it does as long as you know that it's bounded, because it can make something quite funny, which does something like that, or maybe it may have some discontinuity discontinuities, okay? It can do all sorts of crazy stuff, but it's bounded, so that means it never gets above some line, let's call it n, and below some other line, let's call it minus n, okay? And therefore, because it's always between n and minus n, okay, that's the definition of bounded. Whether we can find a number, it could be very large, but a fixed number nevertheless, so that, and for all times of interest, the waveform remains within this band. Okay. So this is fixed, and ICT is always between m and minus m. So therefore, the area of the integral must always be between 2 epsilon m, okay, integral n to epsilon m. And what's happening is you're making this epsilon go to 0. Okay, you make this epsilon smaller and smaller, even though n could be very large. Since it's fixed, at some point this epsilon becomes so tiny that this integral becomes arbitrarily small. And in the limiting case, it gives us 0. Therefore, once again, once you know that the signal is bounded in some interval of length almost 0 or infinitesimally tiny, then the integral of that waveform throughout that special interval is always 0. Okay. So, since this is 0, that means Vc0 plus equals Vc0 minus. Therefore, Vc0 plus equals Vc0 minus. And Vc0 minus was 0. Hence, Vc0 plus is 0. So we figured out Vc0 plus. In other words, capacitor voltage, even though the input is discontinuous, does not experience any discontinuity itself, does not jump from a value to another. And then let's figure out the remaining quantities, IR0 plus and VC0 and IC0 plus. At t equals 0 plus. Okay. Okay, this is the circuit. Here we had 3 ut. Now we're talking about some particular time, which is t equals 0 plus. At that particular time, this provides 3 current, because it provides 3 current at any positive time, and 0 plus is by definition a positive time. Therefore here we have 3 amps. We don't have to write 3 ut. Okay, t equals 0 plus, we have 3 amps here. This is IR. This is IC. Okay, 1 over 1/2 phi. So what we know is VC 0 plus equals 0. Therefore, all these voltages are 0 because there is a single voltage. Everything is parallel. 0 voltage drop across the terminals of the resistor means that its current is 0. If this current is 0, it means that this behaves like an open circuit. And if this behaves like an open circuit, it means that all this 3 amp current is flowing over the capacitor. And we're done. So this means IR 0 plus equals 0. No current passing initially over the resistor. And this is 0, this is 3, therefore by KCL, IC 0 plus must be 3 amps. Okay. Now, in the second part, we were asked for the same quantities, but this time for 4 volt of initial capacitor voltage. The approach is exactly the same, and I leave this part as an exercise. Okay? And the answer is is as follows. VC0 plus is 4 volts. IR0 plus is 4 amp, and IC0 plus equals minus 1 amp by KCL. Well, the important thing is that, again, using the same argument, the capacitor voltage, because its current is bounded, the capacitor voltage will not feel or will not experience any jumps. That is, if VC0 minus is 4 volts or anything, VC0 plus equals that thing. And once you have VC0 plus, you have everything at T equals 0 plus. Therefore, it's not really even an exercise, just a one-line solution. Okay, now let's make things a little bit interesting by introducing a more interesting source than a step. Okay, so I'm talking about impulse or delta function. This is our next example. Again, the same topology. The only difference, which is not that small of a difference, is that now we have an impulsive current. Okay, so this means if you integrate this, you have 1. So what this does is, in an infinitesimal time interval from 0 minus to 0 plus, this current source pushes one coulomb of charge to the rest of the circuit. Okay, and then that charge will have to go somewhere, and once it gets to those places, the currents and voltages clearly will change. This is our circuit. 3 parallel components. Initial capacitor voltage is something which we denote by V0. Okay, minus 6 volts, plus 17 volts, whatever you like. And then find, in terms of V0, VC0 plus, IR 0 plus, and IC 0 plus. Okay, we're going to figure out those quantities just after this impulse does what it does. Okay. So let's do the analysis in this tiny, infinitesimally small interval. Again, we invoke substitution theorem and replace the capacitor with a voltage source under the assumption that capacitor voltage is always bound. Therefore, that voltage source will provide only bounded voltage. This is IC, this is VCT, this is IR, and here we have the impulsive current. Okay. Again, we recall our assumption, which says that stored energy in a capacitor or inductor is always finite. Finite stored energy. Since energy is 1/2 C Vc squared, gives us bounded capacitor voltage. And then, using this topology, we're working with. Bounded capacitor voltage means that the voltage of the resistor is bounded because they share the same voltage, and then by Ohm's law, the current passing through the capacitor, the resistor is bounded. Okay. So bounded IRT. And now let's figure out the consequences of the fact that the current over the resistor is bounded. So what we do is what we did before in our previous example. We write the terminal equation for the capacitor. VC0 plus equals VC0 minus initial time, final time. And the reason that final time is 0 plus is because we're interested in these quantities at that particular time, t equals 0 plus. Okay, plus 1 over the capacitance, which is given to be 2 farads, and then you integrate throughout the interval of interest the capacitor current, okay, ICT dt. Okay, so what's capacitor current? Well, we don't know what it is exactly, but let's try to express it in a different way, and perhaps when we do that, certain things will become clearer. Now, initial voltage is given to be V0, okay, let's say 6 volts, plus 1/2, 0 minus, 0 plus. And now, using KCL, let's express IC in terms of the currents of the other two components. Okay, so then we have delta T minus IR T dt. Okay, because the current of the current source equals IR plus IC, therefore IC must be this difference. Okay, and then let's write this as two separate integrals. We have the constant term, we have 1/2, 0 minus to 0 plus, delta T dt, and minus 1/2, 0 minus to 0 plus, IR T dt. And IRT, we don't know exactly what it is. Okay, but because we're performing the integration throughout a very special interval, that is an interval of length infinitesimally small, we don't have to know exactly what IRT is. All we have to know is whether it's bounded or not. And we do know that it's bounded. Therefore, you integrate a bounded signal in this interval from 0 minus to 0 plus, which has arbitrarily small length, and this is negligible. Okay, therefore it keeps we can replace it with 0, and once that term is gone, we know the result of that integration. By definition, this is 1, and then we have 1/2. Therefore, VC0 plus must be VC0 minus plus 1/2 volts. Okay. This is 1/2, and this equals 0 because IR is bounded. Okay. Hence, VC0 plus must be whatever initial voltage you add to it, 1/2 volt plus 1/2 volts. Okay, and then once you know this voltage at T equals 0 plus, you know everything at T equals 0 plus. Let's figure out the remaining quantities that you were asked. At T equals 0 plus, we have the resistor, the capacitor, and the impulsive current source. Now, the impulsive current source is or does the interesting stuff only at throughout the interval between 0 minus and 0 plus. Once you're to the left or right of that interval, then it's just 0. And since here we have a current source at t equals 0 plus, our current source is providing 0 amps of current. And the current source that provides 0 amps of current is no other than this open circuit. Okay, so here we have IR, and here we have IC, 1 ohm to F. IR 0 plus equals VR 0 plus over the resistance. VR and VC, they're the same because they're in parallel, therefore IR 0 plus equals VC 0 plus over 1. So that yields V0 plus 1/2 amps. And IC 0 plus then is IR plus IC equals 0. Therefore, minus that is the capacitor current, clearly. Minus IR 0 plus, and that's minus V0 minus 1/2 amps. Okay, now we will talk about a little shortcut which will simplify our analysis. And for that we have to realize the key point in our analysis, and the key point in our analysis was that the capacitor voltage was bounded. Okay. Everything grew from there. For this interval from 0 minus to 0 plus, we obtained ICT equals plus minus IR. So that was by KCL, and that we can write as plus minus VCT over R, because VC equals VR, and then we can transform current to voltage, the capacitor voltage, as such. Now this is the impulsive term, and this is bounded term because the capacitor voltage is bounded. Note also that bounded term has no effect on the value of VC0 plus. Because we integrate from 0 minus to 0 plus, and then because it's bounded, whatever it is, it will always give us 0 answer, and therefore the only contribution will be coming from the impulsive term. Now, since any bounded voltage source instead of this independent voltage source, which we use to replace, thanks to substitution theorem, the capacitor, would yield the same impulsive term. The same impulsive term. We can replace this device or this voltage source in our circuit of analysis with the simplest bound voltage source. Okay, the simplest bound voltage source is the voltage source that provides 0 volts at all times, and the voltage source that provides 0 volt voltage is no other than short circuit. Okay. That is the short circuit. To compute the impulsive term of the capacitor current ICT throughout the interval 0 minus to 0 plus on the interval from 0 minus to 0 plus. Okay. So let's revisit our example with this suggestion here, which says that now, since the only thing that matters about VCT is that it's bounded, it doesn't make any difference, okay, as far as figuring out impulsive term of, or the impulsive component of the capacitor current, what voltage source that you choose, okay? You replace that voltage source with any other bound voltage source, and it may not be giving VCT, whatever the capacitor voltage is, still you will get the same impulsive term. Okay, so therefore, if that's the case, why not use the simplest possible bounded voltage source, okay, for our analysis? And that's the simplest possible bounded voltage source is short circuit. So with that suggestion, let's revisit our example. And what we're trying to do is we're trying to figure out capacitor current for the interval 0 minus to 0 plus. Okay, for the interval from 0 minus to 0 plus, we consider this circuit, where the capacitor is now replaced by short circuit. This is 1 ohm, this is IR, and this is IC. Okay, since this is short circuit, and this is some non-zero resistance, all the current, clearly, will flow over the short circuit. Therefore, IC equals delta of T. IC of T equals delta T, the impulse, and that yields VC0 plus equals VC0 minus, which is V0 plus 1/2, 0 minus 0 plus IC, which is delta T dt, and that's V0 plus, the result of that integration is 1/2. Okay. Oops. Same as before. Now let's consider the last example for this lecture. our final example, we have no source, only a capacitor and an LTI resistor, and also a switch. So initially the capacitor is charged and it produces some voltage which we're denoting by V0, and since the switch is open, the current is zero. Current zero means that the voltage is fixed. Okay, so the capacitor is waiting at this constant voltage V0. Okay. And then at t equals 0, the switch shuts, and all of a sudden this capacitor and that resistor becomes in parallel. They're connected, or depending on how you look at it, they become connected in series. Okay. And then that connection starts or forces certain things to change. Okay, the voltage, it generates some current and the voltage starts changing. And now we will try to figure out what happens to all those quantities, those variables. Now, for that, what we need is the circuit at t equals 0 plus, which is, well, switch shut, therefore this and that, they're in parallel, and okay, and we need the initial condition at t equals 0 plus. Okay, so we have to determine, therefore, whether this switch introduces any jumps in discontinuities at the capacitor voltage. Okay, or put more simply, whether VC0 plus equals VC0 minus. Okay, now I will leave to figure that out to you. Okay, I'm a student. It's not difficult to see that VC0 plus will be same as VC0 minus. The capacitor voltage will not make a jump due to the closing of the switch. Okay. Equals V0. Let's call this equation 1. Now here put a question mark for you to think about that. Okay. And now for times after the switch is shut, for t positive, let's write down things that we can using KCL, KVL, and terminal equations. First of all, VC equals VR, okay, because the direction of the current is given as such, and that equals R times IR. Okay, the capacitor voltage is related to resistor current through that relation. Also, we have the terminal equation for the capacitor, which is C dVc dt. And finally, we have, due to KCL, the relation or the constraint to be satisfied by the currents. IR plus IC must equal 0 after the switch is shut. Even before the switch is shut. And then, combining all those three equations, we can obtain a differential equation only in terms of capacitor voltage. And that turns out to equal d over dt VCT equals minus 1 over RC VCT. So that's the first order LTI, okay, homogeneous differential equation. Homogeneous means that it doesn't have any input. It's only in terms of this variable, capacitor voltage in this case. And let's call this equation 2. Okay. And now we have everything we need to write down the capacitor voltage. Not for t equals 0 plus, but for all positive times, for all future. Now 1 and 2 implies what? Okay. Now here we have a differential equation, and it admits a family of solutions, okay? Namely T over RC. Any constant K times this function exponential e to the minus T over RC would satisfy this differential equation 2. Okay? But that's not the only constraint to which our capacitor voltage is subject. It's also subject to the initial condition constraint. Therefore, thanks to 1, K cannot be arbitrary. Okay? It has to be, by applying constraint 1, it has to be V0. Okay? And this is the unique solution that satisfies the initial condition constraint and differential equation constraint simultaneously. Okay? Once we have Vc of t, we can immediately obtain the resistor current, and we have by R of t equals V0 over R e to the minus T over RC. Okay? Supposing that our components are passive, that is C and R, they are positive, and supposing that V0 is also positive without loss of generality, suppose that we start from 12 volts, VCT will have the following shape. Okay, it starts from V0 and it decays exponentially, determined by the decay rate 1 over RC. And 0 by R T. The current will have the same shape, okay, the same curve, only it's scaled by 1 over R. This is V0. Now we have the same shape, but we're starting from V0 over R. So this is the initial current of the resistor. As time goes on, it becomes smaller and smaller. Now, let's figure out other things that we can figure out. Energy dissipated. Excuse me, displaced. And the capacitor during some arbitrary interval, let's say starting from the initial time to, let's say, some t in the future. Okay, 7 seconds or 7 days, whatever you like. So WC 0t equals 1/2 C VCT squared minus 1/2 C initial voltage squared. Okay, V0 squared. Now this is the stored energy at time t in the capacitor, and this is the initial stored energy, and the difference is how much energy is displaced from the capacitor. Okay, and that equals 1/2 C V0 squared. Using the term that we obtained for VCT, we can write this difference as e to the minus 2t RC minus 1. Okay. Now this, for all positive t, is strictly less than 1. Therefore this difference is negative. Therefore this quantity is negative. This quantity being negative means that the energy that equals the magnitude of this difference was transferred from the capacitor to the rest of the circuit. And in this very simple circuit, by the rest of the circuit, we mean that LTI resistor. Okay. So let's put that observation down. Note that VC 0t is negative. Therefore, we conclude energy is drawn, okay, it's extracted from the capacitor by the circuit, by the rest of the circuit. Okay. And by the rest of the circuit we mean, because we have only one other component, the resistor, it must be that energy must be consumed by resistor, okay? And energy being consumed or absorbed by resistor simply means that resistor takes that energy, electrical energy, and transforms it into heat. So the energy escapes from the circuit to the environment, let's say. Energy dissipated on resistor during the intro. Okay. Since energy, it seems, has nowhere else to go but to dissipation over the resistor, we can now check whether that's the case, okay, by computing the energy dissipated at the resistor. If the magnitude of that energy equals the magnitude of this difference, then everything will be fine. Okay, VR0T, the energy dissipated over resistor for the interval 0 to t. And that equals the integral of power, because power is the rate of change of energy. IR tau VR tau d tau. Okay. This is PR tau, let's say, the power of the resistor. Now that equals, we know IR of t, and that's for VR of t, because R and C there in parallel, we also know that it's V0 e to the minus t over RC. Therefore, we know both terms, that means we know the power, and we can compute the integral. So that equals V0 squared over R, 0 t e to the minus 2 tau over RC d tau. Okay, and that's V0 squared over R, 2 e to the minus 2 tau over RC evaluated from t equals 0 to t equals t. That yields 1/2 CV0 squared 1 minus e to the minus 2t over RC. Okay. Now that we have the same expression with a little difference, that the sign is opposite. Here we have something negative, and here we have something positive. The sum gives us 0, the sum is always 0, so that means energy is conserved in the sense that whatever energy is extracted from the capacitor is dissipated over the resistor, so everything checks out. So let's finish this lecture with that final observation. Observe VC0T plus VR0T equals 0. Hence, the energy that's being drawn from the capacitor is dissipated, is absorbed by the resistor.